So in this webinar, we'll be seeing three main topics: the elements and processes of the petroleum system, the techniques and types of data used in the petroleum industry, and some of the workflow or some steps of the workflow from basin analysis, so very wide scale, down to a drill-worthy prospect, so the potential accumulation that we want to drill and hopefully find hydrocarbons. I expect this to take about 35 minutes, and then we'll have about 10 minutes of Q&A, but we're flexible with time both for the presentation and for the questions and answers. So the elements of and processes of the petroleum system. There are several elements which are rocks, let's say. So reservoirs are elements of the petroleum system which you can designate as rocks. That's why they are called elements. Also the same for seal and source rock. But then there are other aspects of the petroleum system which are not, you cannot put a hand on them. So they're related to processes that need to take place in order for accumulation to form. Those are related with migration and timing, and also with traps. Traps can be considered as an element because they consist of a geometry of reservoir seal, but they can also be considered to be a process in the sense of a geological process, be it tectonic or sedimentological, that forms a hydrocarbon trap. And we'll see examples of that during this webinar. So starting with the source rock. So the source rock is a rock which is capable of generating hydrocarbons, or it has generated hydrocarbons in the past. It's important to say that these need to be mobile hydrocarbons, so it needs to be in a significant amount that they are generated, and then they are expelled from the source rock and they migrate eventually into a reservoir or up to the surface. So that's where hydrocarbons originate, and they will migrate and eventually accumulate in a reservoir. So assessing the presence and the quality of a source rock is one of the first steps when you're evaluating a basin in terms of petroleum geology, and specifically for its petroleum systems. Lithologically, they will usually, and in most instances, correspond to dark shales, marls, or limestones, and that's an indication of high content of organic matter. Indeed, one of the basic ways to evaluate a source rock is to calculate or to measure the total organic carbon content. It's expressed in percentages. There you'll find many different classifications of the types of source rocks, but usually the number that you are looking for is 1%. So above 1%, you can consider that you have a source rock that will be generating enough hydrocarbons. Below that, it's difficult that source rock is a good source rock. You can have several examples of source rocks having up to 30% or even more TOC, but that's very uncommon. So usually you're around 1% up to 5%. When you have 5%, is already an excellent source rock. We have extreme cases, for example, in coals, where the amount of organic content is up to 100%. But those are very unusual situations, and coals are not that common in the geological record. Another way to evaluate source rocks is to go a bit further on the geochemistry and evaluate the hydrogen and oxygen indexes. And this is a typical plot called the Van Crevelen plot, where you have three main types of source rock. So type 1 will have high hydrogen index and not so much oxygen. And these are highly oil-prone source rocks. So most of the hydrocarbons generated by the source rocks will be oil. These are usually deposited in lacustrine environments and also in some restricted marine environments. Then type 2 are also oil prone, but they also have the capability of generating some gas, which are usually deposited in marine settings with high organic productivity. And finally, type 3 source rocks, which are very high in oxygen index, and they will essentially generate gas. So they have very low potential for generating oil. So that's also a very important aspect to analyze in a petroleum system is the characteristics of your source rock. Another aspect that should be taken into account, especially then when you're dealing with migration and the timing, is the temperatures that these source rocks were exposed to. So up to about 60 degrees, not much is happening. So the organic matter contained in source rocks is not being transformed into hydrocarbons. But from 60 degrees onwards, as it heats up, it enters what is called the oil window. So most of the oil will be generated between 60 and 120 degrees. So that's what's called generally the oil window. And above that, most of the gas will be generated. So somewhere between 120 and 150 or 60 degrees, most of the oil will be generated. This is generally called the catagenesis range of temperatures. Above that, you'll have some gas generation, but it will be mostly dry gas, meaning that it's a very pure gas containing very few fluids, very few liquid hydrocarbons. That's called metagenesis, and it goes up to about 250 degrees. Above that, you're in metamorphic domain, let's say, and there's the source rocks will have generated all the hydrocarbons they can generate. There's no further potential for generating hydrocarbons above 250 degrees. Then with migration and timing, it's a process, so it's not an element of a petroleum system. And we can separate the primary migration, so it's the expulsion of hydrocarbons from the source rock that generated them. This usually happens because you have building pressures in source rocks up to the point where it will basically fracture the source rock and hydrocarbons will escape. You can have a secondary migrations when hydrocarbons move from one reservoir to another, or they move up to the surface. Generally, the study of hydrocarbon migration, and it's also the generation, is called basin analysis, or more correctly, petroleum system analysis, PSA. You can model it in 1D, so if you're using just data from one well, for example, 2D if you're using a seismic line, or 3D if you're using a seismic volume. This is an example of modeling a source rock. So you give it some geochemical properties and you model it over a range of temperatures to understand how much oil or gas it will produce. And then you can include that in more complex modeling, be it 1D, 2D, or 3D, to understand the range of temperatures when most of the oil and most of the gas were being generated, and then how it behaved over geological time. It's also important in terms of timing or the sequence of events that need to be in the appropriate sequence. Otherwise, you will not have an accumulation. So, for example, you need to have trap formation prior or contemporary to generation and migration. Otherwise, you won't have an accumulation. So you can generate all the oil you want. It has no trap to migrate to, then it will not accumulate. It will migrate to the surface, or it will be lost during migration along the way. Also, for example, reservoir and seal need to be formed prior to the formation of the trap and generation and migration. So you can have all the reservoir and seal that you want. If there's no anticline or some fault block or some other structure that can trap the hydrocarbons, so to form the geometry to trap hydrocarbons, the presence of reservoir and seal will not be significant. And this is the typical chart that petroleum geologists produce, where they plot the several elements and the processes of a petroleum system to understand exactly how, when and how hydrocarbons were generated, were migrating, and eventually accumulated. So we're going to see conventional reservoirs. We won't focus much on unconventionals. That's something that we'll elaborate more on the full course. So reservoir rocks are any types of rocks which have the capacity to retain fluid, so be it water, gas, or oil in its pores. Any rock can be a reservoir, so as long as it has some porosity and permeability. And there are examples where igneous and metamorphic rocks are indeed hydrocarbon reservoirs and they are being produced from. But those are exceptions. The vast majority of reservoir rocks are sedimentary rocks. In terms of sedimentary rocks, we have siliciclastic rocks, which are the most common. You have all ranges of grain sizes, from clays up to gravels and even bigger particles, but the vast majority of siliciclastic reservoirs will be sand-sized reservoirs. They can be classified according to their grain size, their composition, and their texture, which is essentially the proportions of the several grains that compose them. So not just the matrix, but also the cement and the matrix which is filling this interparticle space. With carbonate reservoirs, they're a bit more complex to analyze, especially when you're interested in their reservoir characteristics. They're frequently not transported or not significantly transported, so it's common to say that carbonate sediments are born and they are not made. So that happens in usually platform settings or shelf settings, where you have commonly high temperature or warm waters, and calcium carbonate and other carbonates are precipitated either directly from seawater, or they are the carbonates are precipitated by organisms that produce some kind of shells. These can be microorganisms, and they will precipitate from seawater and create algal mats, for example, or larger organisms like bivalves or rudists in the geological past. Many reef fauna will produce calcitic particles, and they will contribute considerably to the amount to the deposition of carbonate sediments. There are many classifications of carbonate sediments. One of the most used is this of Dunham, which emphasizes the proportions of matrix or cement and the grains. So they will be considered to be mudstones, waxstones, packstones, or grainstones, considering the proportion of mud, so the finer particles, and the grain, so any calcitic particles which of larger dimensions that are part of the rock. And in cases that you have, for example, algal mats or stromatolites or other that same type of carbonates, they are called bound stones. Another one which is commonly used is the one by Folk, and that can be used in conjunction with the one by Dunham, which emphasizes the type of cement and matrix, and also the grains that compose the carbonate rocks. So micrite, if it's composed essentially by mud, but then it can be biomicrite if the grains which are contained are biogenic particles. They can be constituted by oolites, and it will be depending on the composition of the matrix. They can be oospirite or oomicrites, biospirite, biomicrites, and so forth, depending on the type of particles and the type of cements. So there are many types of classifications, but these two are the most used by far, the Folk and Dunham classifications. And then there are, of course, other characteristics that can be included in the description of a carbonate rock. they're poorly or well sorted, densely packed or sparsely packed, and so forth. Irrespective if it's a siliciclastic or a carbonate reservoir, the two most important properties that are described in reservoir rocks are the porosity and permeability. Porosity is generally defined as the pore volumes versus the total volume of rock, so the amount of volume which is occupied by the pore space. There are different types of porosity, so you can have absolute porosity, so all the pores which exist on the rock, in the rock, versus the total volume of the rock, and also the effective porosity. And this will be the most relevant for petroleum geology, which are it reflects the volume of interconnected pores. So if you have pores which are not connected among each other, they can even contain hydrocarbons, but they cannot be produced, you cannot extract them. So we'll be interested in the interconnected pores, so that's what is called the effective porosity. Reservoir porosity varies greatly, and in reservoirs it can vary anything from 35%. Above that it will be difficult to have a rock sustaining itself, so we start having the grains composing the rock not touching each other. And that happens in poorly consolidated sands. And you can have something less than 10% in low-quality reservoirs. In carbonate reservoirs, especially if they have high permeability, then you can have porosities which are even lower, than down to 6% or similar values. Then there are different types of porosity. So primary porosity will be the most relevant for siliciclastic reservoirs. That's to do with the pore space which exists interparticle, so between particles. But then there's secondary porosity, which is produced during after deposition and during diagenesis. So you can have dissolution, dolomitization, all kinds of fracturing, all kinds of processes that create additional porosity. This will not be very relevant in siliciclastic reservoirs, but it will be extremely important in carbonate reservoirs. And frequently that's the main porosity type that you find in carbonate reservoirs. Then permeability, it's a property that is directly related to porosity, but it reflects the capability of any material to be, for a fluid to be transported along that material. Applied to rocks and in the oil industry, you usually use darcies or millidarcies. And the permeability of reservoir rocks varies anything from 0.1 millidarcies up to 10 darcies in exceptional cases. So it has to do with the porosity, but frequently what you find is that permeability can be enhanced, for example, by fracturing. So fracturing can have a limited effect on the porosity, so it's not really creating a lot of pores, but because it's connecting the existing porosity, it will enhance permeability in very significantly. It's also relevant to look at texture because permeability may not be the same in every direction. So if you have lamination or directional fracturing and so forth, you can have different types of permeability depending in the direction you look. So when you're thinking of producing from a reservoir and the way you drill wells, and eventually if you are using fracking to produce from your well, you need to understand fracturing in detail. So permeability will be extremely important. Seal rocks and seal capacity. So seal, and sometimes also called cap rock, is the element of the petroleum system that prevents the migration of hydrocarbons. So they are impermeable rocks, so they will have very low permeability. They usually correspond to ductile rocks, so they will tend to bend, to fold with tectonic pressure or events, rather than to fracture. And the seal will be as good as the amount of pressure it can sustain, so the oil column it can sustain and the corresponding pressure. There are several classifications of seals, this is just one of them. So the type A seals will correspond to salt, anhydrite, and some organic-rich shales. And these will be capable of holding very high hydrocarbon columns and the corresponding pressure without fracturing. Even thin sequences or thin layers of these types of rocks will be able to hold very high hydrocarbon columns. Then type B includes most of the shales that you encounter in the geological record, and these are usually also good shales, but you need a significant thickness of these rocks in order to sustain hydrocarbon columns and the corresponding pressures. Then other types of seals which are not that effective, like sandy shales, siltstones, and other types of rocks, which are only effective seals when you have very short, very low hydrocarbon columns and very low pressures. So this can be effective seals, for example, when you have very shallow hydrocarbon accumulations, and these types of rocks can actually hold the hydrocarbon column because the pressures are considerably low. Usually what we look for is either evaporites like salt and anhydrites, or these shales. These are usually what are considered effective seals. So you can have different types of seals. In simple structures like this anticline, for example, you only need a top seal, so you need a stratigraphic unit above the reservoir, stratigraphically above the reservoir, in order to produce this accumulation, considering you have a trap. In other situations, you will need not just a top seal, but also lateral seals. So you will need some kind of sealing lithology stratigraphically above and below the reservoir in order to create this accumulation, or to hydrocarbons to be retained in this area. Structural and stratigraphic traps. So these are the two main types of traps. They can be very varied in terms of geometry, and they require that they contain a reservoir and seal, so that they can create an effective trap. Otherwise, you can have beautiful anticlines, but if you don't have a reservoir and a seal, you won't form a trap. So structural traps are usually the ones that petroleum geologists look for. They're the easiest to identify on seismic and even sometimes in outcrop data. They can be simple anticlines like this, for example, or fault blocks in case that seal is just posed against a reservoir rock and you can create an accumulation there. There are other examples of structural traps, like, for example, three-way closures against salt, three-way closures against a fault. In this case, so you have a fault block here which is creating a trap, or the simplest of them all, that you have an anticline, so it's a four-way closure. Stratigraphic traps are usually more complex, and they're usually not that easy to identify or to recognize and then to describe and characterize. There are four main types, and you'll find other types of classification. But here, for simplicity, I'm just using these four: so depositional, erosional, diagenetic, and fluid types of trap. The geometries can be very varied. Usually, they can involve an unconformity, but they can also be a lateral facies variation. There are many types of stratigraphic traps. I'll just show two examples here. This from two seismic lines. So here you have a complex erosional surface, and you have this, what is called in the petroleum industry jargon, buried hills. So these remnant structures, which, if they contain any reservoir rock here, and if the later rocks that were deposited around them are sealing, then you can create an accumulation here in this buried hill. This is another type of stratigraphic trap where you have this unconformity, which eroded a previous stratigraphy. And these Albion reservoirs, now we know, we've drilled through them, we know these are sandstone reservoirs. And the rocks deposited above them are mostly shale, so they will be a seal, and you have an accumulation forming here. In this case, it's not just stratigraphic, there's a structural component. So these are tilted strata, which help to form here the trap in this location. There are many, many types of stratigraphic traps. I'm showing only 2 examples. Techniques and types of data which are used in the industry. So this is enough for a full course on its own. We'll see only a few examples. The basic thing that you can do is to study outcrop data, and that sometimes also includes seeps. That's when you have hydrocarbons migrating up to the surface. When you find that, you have several elements of and processes of the petroleum system that are proven. So you've proven that there's a source rock, you've proven that there's generation and migration, and in part you've proven that there's timing. You cannot prove with that you have reservoir, trap, or seal. For that you need to use other methods. So you can have seeps if there's an accumulation near the surface and the reservoir rock is actually outcropping, so it acts as a carrier bed up to the surface. You can have a fault that provides a migration pathway up to the surface, or you can have seal fracture of an accumulation. For example, here, if the seal was fracturing, you could have an escape of hydrocarbons up to the surface. You can actually see them at the surface. This is an example from a very well-known area in California where you have this bitumen at the surface. This is basically oxidized petroleum oil reaching the surface. So these are very obvious examples. In other cases, it's not so obvious, and you may need to do, for example, examine soil samples to try to understand if you have hydrocarbons reaching the surface. This is an example from Azerbaijan. I'll play the video, not all of it, but just to show where gas is actually reaching the surface, and it's basically on fire. So this is an area where it's continuously burning, and it will continue burning until all the natural gas that is reaching the surface is exhausted. This is actually tourist attraction in Azerbaijan, and you have other examples around the world where this also happens. You can also find gas and oil seeps offshore, so you'll have something reaching the seabed, and they'll be released into the oil column. Because of density, they will float up to the surface, and you'll find an oil slick at the surface, and these can be identified using satellite images, and you can also study a petroleum system based on that. And of course, outcrop geology. If you have access to outcrops that are either analog or are lateral equivalents of the rocks you are observing in the subsurface, then you can study them for the source rocks, the reservoirs, and all the petroleum system elements. Seismic techniques, again, this is enough for a full course. I'll be very brief on this. So seismic is one of the basic tools that petroleum geologists use, and geoscientists in general. In a very basic, very simplistic view, it's a way to image the subsurface. You have an emitter, a source of seismic waves, acoustic waves, which is shooting onshore or offshore. These seismic waves penetrate the surface, and they are reflected by the several layers which exist in the subsurface. The reflected waves are then collected in hydrophones or geophones, depending if you're onshore or offshore. And with that, you're able to build a seismic image. That's for 2D. If it's a 3D acquisition, then the apparatus is a bit more complex. You have sources of the acoustic waves, and then an array of hydrophones which collect the reflected waves. If you're onshore, then the common use is these vibroseis trucks, which produce, with this device here, it produces a seismic wave into the subsurface, and then you have geophones collecting the reflected waves. That this is a ultra simplified workflow for you from the raw data until you actually have a seismic image of the subsurface. I'm not going into the details. It's a rather complex and laborious process until you can actually get an image of the subsurface. When you do have seismic, then you can observe all the subsurface, and of course, depending on the quality, you can observe many aspects of subsurface geology. One of the basic things that you can map out are seismic horizons. In this case, a very bright reflector is usually the seabed, but you can see other reflectors in the subsurface that you can map. And you'll be looking for your reservoir and other elements of the petroleum system in your seismic. When you have good enough seismic, especially when you have 3D seismic, you can actually try to understand where your reservoir is, so more sandy lithologies, which will have a different seismic response compared, for example, from more shaly lithologies, which will have a different seismic response. In this case, it's simple amplitudes of seismic signal, but they are very, very useful to characterize the subsurface. In this case, a lobe of sands was mapped and it could be differentiated from the nearby sands. And with that, we have an idea of the reservoirs and we can have an idea where we should drill. You can, of course, map faults as well. They're usually depicted on seismic as discontinuities of the seismic reflectors. They can be seismic reflectors themselves, but usually what they are visualized as discontinuities in the seismic reflectors. And you can also map the horizons and use different types of attributes to be able to image, in this case, in the plane view, in the Z view of the fault traces, and with that map the faults in detail. So you can use seismic sections in 2D, so vertical sections, and also horizontal slices, such as this one, to map faults. Seismic data can also be used to characterize reservoirs in detail. For example, if you have well data and you can match porosity measurements with some kind of seismic property, in this case it was impedance of the seismic data, then you can extrapolate from your well into the rest of the seismic volume, in this case the porosity properties. There are other examples where you can also extrapolate, for example, the TOC content of your source rock. If you can associate that confidently to a seismic property, then you can also extrapolate that and to the rest of your seismic data and understand where you may have sweet spots of TOC and where the source rock will be more prone to be generating oil or gas. Exploration wells and downhole data acquisition, that's the second type of data which is most used in the oil industry. I'll show a short video. Basically, when you have a borehole and you send a probe which collects physical data from rocks, and this is electrical data, gamma ray data, acoustic properties, all sorts of data which are recorded either passively by recording apparatus in the tool, or by other methods which basically shoots either an electric system or acoustic signal into the rock, and then it's recorded by the same tool. Then different types of properties will have different types of resolution and penetration into the borehole wall, and those can be analyzed. Then different types of rock are already known to have different characteristics in terms of density, neutron, acoustic properties, resistivity, and so forth. And with that, along a borehole, along a well, we can identify, even if we don't know the geology, even if we don't have the rock pieces which are produced by drilling the well, we can have an idea of the lithologies, if they contain oil, water, gas, and all different sorts of petrophysical properties in a well. And with that, we can estimate the porosities, the amount of hydrocarbons, and so forth. There are other exploration techniques such as aeromagnetic gravity, CSEM. I will go very briefly with that. So you can measure gravimetry data. For example, when you're doing seismic acquisition, you can add a gravimeter to measure that. You can also measure geomagnetic properties of the area that you're surveying. These two examples are offshore, but you can also do that onshore. Usually you use helicopters with a probe, which is towed at a specific distance from the surface, and with that you collect the data. And that can be very useful used together with seismic data. We'll now see a bit of the workflow, or a simplified version of a workflow from a very broad scale, so basin scale down to a drill-worthy prospect. This is what is called an exploration funnel, and it's called like that because usually you go from many different opportunities, and with each step you narrow down your focus until you're down to one or only a few opportunities that you really want to drill. So each company has different strategies regarding how they look for new projects. For example, for large companies, if they are vertically integrated, for example, they may have a refinery or gas stations in a country, they may be interested also in having exploration blocks in that same country. The strategy can also be to expand its activity in a region or a continent. So, for example, a company may be interested in exploring in West Africa or in Brazil or something like that. So they will invest their efforts, they'll put their efforts in that area. Or they can be experts in a basin and they will only chase opportunities in that specific sedimentary basin. They can also explore for a specific play, so a type of accumulations that they know they have the know-how in-house, and so they only explore or they are only interested in opportunities that include that play. They can define a geographic area, they can define a type of projects, they can be interested in low-cost projects onshore, or they can be interested in high-risk, high-reward projects in frontier basins, in places where there's very little information and few companies have explored there. They can also grow organically, so with new projects, or they can buy out a company which is already active in the area where they were interested in. Usually these teams are called new ventures or new opportunities, and they are composed not just by geologists, but usually engineers and also commercial people, so economists or other areas of expertise, which need to work together to understand where the company needs to invest. This can be bid rounds, so a country can open a bid round over an area and define blocks of exploration, and then companies can bid with money or tax returns or different criteria, and the best offers will be chosen by the government. That can also happen with farm downs or farm outs, so a company is interested in divesting their assets, so they can sell part or complete the whole participating interest in an asset, and other companies will be interested in buying it. Some governments have an open door policy where companies can come in directly and negotiate an area or a block directly with the government. And as mentioned before, they can also companies can also buy other companies which were already active in that area. Once the opportunity is identified, the assessment is based on the available data. Usually there's some data provided by either by the companies or the governments which are promoting the opportunity. That can be regional data, so any geological studies in the sedimentary basin will be interesting. Existing data, seismic data, 2D or 3D of the area will be relevant for the evaluation. Well data, so any well drilled in the area will be relevant to analyze the several petroleum system elements and processes. And of course, if there's any discoveries or existing fields, producing fields in the region, those will be relevant as well. In addition to the data provided, companies may want to add more data to their data sets to evaluate properly before they actually make a proposal. So many companies have their homework done, so they study a region even before a bid round is open, so that when the opportunity arises, they are already ready to analyze and only update the study that was done before. It can also happen that large companies that were active in a region, they abandon the region and then they come back. That can be because there's new data, there's a new idea, or simply because they were active in the region when the technology only allowed to explore in a certain area and not in others. For example, for ultra deep water exploration, which is now possible, and a few decades ago it was not possible. If this is the case, then some of these companies may have competitive advantages, and that happens with very large companies that exist now for many decades and have data from all over the world. So if a company is interested, they will make a proposal to enter the block. That decision needs to be made in conjunction with a commercial team. It's not just geology. And the two types of assessments need to be worked together. So a commercial team may say that the terms are not that good, so we should only look for big accumulations. So that's an indication for the geologist's team to know what they should look for, or that they should only look for accumulations near existing infrastructure. So there's this type of feedback that different teams need to have. So if there's a positive evaluation, proposal is done, a company may win that bid, or it may lose it. So that's already a stage here where many of the initial opportunities will only correspond to a few actual assets gained by each company. The steps usually when there's a block which is acquired by a company, you study the regional data, outcrops, any available data will be relevant, regional 2D lines, and any geomagnetic gravimetry data may be relevant, and you can in some cases ask for additional 2D data more restricted to a specific area. So the team will start mapping leads that can be matured to prospects, but then there's a seriation that needs to be made. And the two criteria are usually risks and volumes. So only the leads with greater volumes and lower risk will move forward to the next stage. So in this case, these here will probably not move forward, only the ones with higher volumes. They may have significant risk, like these two, for example, but the volumes justify that they move to the next phase. So here we're into prospects, and then there's a second stage of evaluation. The leads are mapped in more detail. They are matured into prospects. Frequently, there's the request of acquiring 3D data for a specific area. There's a lot of geological studies which can be performed on the geophysical side and also engineering side. And more additional studies can be proposed if technically justifiable. So from the initial prospects, it's common that with the new evaluation with the further data that the volumes and the risk change. Sometimes for the good, sometimes for not so good. Also happens that some of the prospects with initial engineering analysis, they can be eliminated. For example, if prospect D was too deep in terms of water depth to be drilled, it can be discarded completely because it's just not possible to drill there. Frequently, it happens that volumes go down when the evaluation is done in more detail. The risk can go up or it can go down, it depends. And it can also identify new prospects that were not identified before. So at this stage, only drill-worthy prospects will be moved to the next phase. At this stage, there's still a lot of geological studies to be made, so prognosis of the well, defining the TD, so the total depth, sample campaign definition, and so forth. But there's also a lot of non-geological work that needs to be done by the drilling engineers and also the facilities to understand the land base for the drilling rig and so forth. Usually there's a decision tree to define what should be done. This is a super simplified version. Usually they're much more complex. So if you're drilling the well, if you have evidences of hydrocarbons, if no, then you abandon the well. It was unsuccessful. If yes, then you may want a production test to understand if you can produce the hydrocarbons that you found. If the result is poor, then you can abandon the well. You're not going to develop that accumulation in a commercial way. If the production test is good, then you will analyze the results and you can maybe keep that well for a later re-entry and turn that into a producer and injector well. And you can start thinking of second wells for appraisal or to drill nearby prospects. Then a graphical view of this workflow. This is a basin that extends onshore and offshore. A few blocks are available in a bid round. Only few data is available, so regional 2D lines, very long and vintage, so not very recent, and only a few wells. So the analysis is done. A block is selected. In this case, it was this one. Acquire the rights to that block. You start studying the geology. The first step would be if you have outcrops of that same basin, you'll study those to understand what you'll find in the subsurface. You'll probably ask for a first 2D campaign, 2D seismic campaign, and that will include not just the block but areas around it so that you understand the regional geology. You may already have an interest in a specific area, so you may ask for a second, more refined 2D acquisition. You map a few leads, and then you may ask for a 3D seismic survey to cover that area. And this can be restricted only to a few leads if you think those are the ones that can be actually drilled. Then drill-worthy prospects are selected. For example, D here, it's over 4,000 meters depth. Water depth, it's not drillable today with the current technology, so that can be discarded, and a few others can be discarded because geological or technical or other technical reasons. So these 3 prospects were selected to be drilled. There's an overlap here between these 2, so you can probably drill a well that drills through these 2 wells, these 2 prospects. So this will be definitely a first candidate to drill. If you can test more than one accumulation with a single well, then that's an obvious candidate to be drilled. If the results are good, then you can start thinking about drilling the second well here in prospect A. So that's the workflow in a nutshell. Of course, this can last for several years and it can be much more complex. But overall, those are the several steps that you take until you drill a well, all the way from analyzing a basin or a group of basins.